All right. Welcome, everybody. Okay. So my name is Gary Shigalov, and this is Piyush. We are both from Twitter. I work on the experimentation team, and Piyush is from the data platform. Today, we're going to talk about the Slim Scalding project, which aims at optimizing memory consumption on our Hadoop clusters. So we started this project as a small Hackwick prototype end of last year, and some of the members of the team are present here, like Anton and Vishali, and Soramki from the JVM team helped us as well. So it started as a small project and now turned into a full-fledged auto-tuning project that is actually spearheaded by Anton, and he has a pull request out on our GitHub, which you're welcome to comment to. So the outline of our talk will be as follows. We will first introduce the use case of my team, which is experimentation at Twitter that powers A/B testing for various product features, and the challenges associated with trying to scale it to our needs. And later on, Piyush will walk you through our infrastructure setup and how to will present the ultimate solution to this problem and introduce auto-tuning. We will conclude the talk with the outlook into our future work, and we will open the talk to a Q&A session. So let's first talk about the experimentation. Experimentation is very important for evolving all features of the Twitter platform. So we measure all kinds of metrics associated with either platform popularity, its performance, and various business metrics. Overall, there are thousands of metrics owned by different teams, and each team is striving to improve the metrics of their components. So they usually work in the following iteration loop. They try to build a hypothesis, what kind of metrics they want to move in the positive direction. They define the success criteria for this particular feature they're working on. They test the hypothesis with an A/B testing experiment. They learn from it and decide whether to ship or not to ship. The changes we're talking about can be incremental UI changes, like replacing, for example, the fave button by likes, or it can be evaluation of machine learning algorithm that power the ranking timeline, or ads recommendations. The point is the faster you make this iteration go through, the more agile is the development of the Twitter product. And so we're striving to optimizing this. End of 2015, early 2016, we published a series of blogs about experimentation at Twitter, and this is the slide of technical overview of the pipeline. In the middle of it is the final product that product managers and product developers use to evaluate their experiments, called the DDG dashboard. It's a web app. So they see a diff of metrics and see whether the metrics are moved significantly, statistically significantly. So this diagram describes how data gets into this dashboard. So on the end user side, we have mobile clients and other Twitter-operated software that calls into a feature switch service that buckets users into control treatment buckets and makes certain features enabled or disabled. There is an instrumentation code on each of this client and even on the backend services that generate events that allows us to measure performance of the product. And we feed these events into the event ingestion service that is connected to the Heron topology for real-time debugging. But the bulk of the processing is done on the Hadoop side using a Scalding-based pipeline. Ultimately, the summaries of metrics are written in a conventional database system that backs this web-based system. It's a very interesting topic in and of itself, and members of my team speak often at various meetups dedicated to A/B testing. But as far as this talks goes, it's just costs, which affects the bottom line of Twitter, and we want to reduce it. So to remind what the Twitter infrastructure looks like from the previous Hadoop Summit talks, we have multiple data centers, multiple clusters with over 10,000 nodes. Most clusters are multi-tenant and host different use cases. We are on Hadoop 2 since 2013. We have more than hundreds of petabytes of data, and we run several tens of millions of containers per day. In order to keep us users of Hadoop, like the Pi team, in check, the Hadoop team imposes quotas for both storage, that is file count and storage space, as well as the compute volume, which is controlled by a yarn queue. And currently, mostly the main memory dimension is used, but I'm in the process of adding CPU, disk, and network dimensions as well. In order to make it easy for the product teams to comprehend how much infrastructure they consume, there is a chargeback function that presents basically our footprint in terms of dollars, which is very easy to understand. So we face every now and then we have to evaluate the SLA requirements that are posed to us by product teams and what price we are willing to pay to achieve the SLA. So on the one hand, we want to deliver experiment results as fast as possible, but obviously there is a infrastructure cost associated with this. So to sort of understand how we can approximate the calculation for SLA, let's look at this picture. So you have a bunch of workload on the top of this sand clock expressed with a typical Hadoop compute counter megabyte millis. So we are looking at the SLA of a single batch. We have some queue allocated to our team, and basically this is the queue here. So we want to push through this sand as fast as possible, and so the elapsed time is this ratio of batch, the workload divided by the capacity. So then we just look at the compare elapsed time to the agreed SLA, and if we're within the SLA, that's all fine. But if we're not, so there are few things that we can do. We can either put less stuff into the top, or we can widen the middle part. Obviously, widening the middle part means that we increase our footprint on the cluster, so the bottom line that we produce affects negatively Twitter's infrastructure costs. So we don't want to do that. So that's why we don't increase the minimum MB. But we can try to put less sand here, and this we can achieve by either optimizing algorithms that will make sure that each container runs faster, or we can reduce the requested memory. So let's assume for the sake of this talk that we did the best job possible on number one, and we're only interested in decreasing the memory footprint. So you can, if you run MapReduce jobs often, you know that you can look at various counters and see how your job behaves in comparison to what you request from the cluster. So you can look at the counter like committed heap bytes that tells you what was the actual usage of the Java heap. and compare it to the maximum heap size that you requested. And if your garbage collection overhead is small, then you know that you can try to tweak the XMX. And in our case, we actually realized that often XMX is twice as needed. So okay, this is the realization, so let's just go and tune the pipeline. However, the pipeline looks rather complex, and there are thousands of jobs involved even in our use case. So it's a tedious task, and by the time we finish tuning manually last node in this DAG, the pipeline might change. So there is obviously some need for automation. So first, it's a quick explanation why the pipeline is so complex. It's because we have tens of thousands of metrics. We run thousands of experiments, and we have millions of users per experimentation bucket. And this is also comes from different sources with various velocity. So you don't want slow sources hijack and hold hostage the fast sources. And so we split them into various partials, so you can think of them as threads in the thread pool, and they fulfill different SLAs. So the critical metrics and core metrics should be computed very fast, as fast as possible. So given this daunting task, we came up with an automation idea and turned to the data platform to help us with this project. And Piyush will walk you through the rest of the presentation.
Thanks, Kira. So I'll probably get started with giving you guys an introduction to Scalding. Scalding is basically a library that we've built at Twitter. It's a very popular library. A lot of people use it in the community. And it's basically used to run MapReduce jobs. It's built on top of another library called Scalding. It's basically a Scala DSL that helps you do that. Since this is a Hadoop Summit talk, I thought your day would be incomplete without a word count example. So here's a word count example in Scalding. So as you can see, we've got, you can read from various sources and stuff, and those are created by the typepipe.from. In this particular case, we're reading from a text file on HDFS. You can run a bunch of transforms on it once you've loaded up that type pipe, like flat maps, group bys, and size operations and stuff. And when you're done, you can write the results out either to another location on HDFS or JDBC or whatever your sinks might be. If you're familiar with the Scala collections API, Scalding is fairly similar. Like you wouldn't probably get too surprised by what you would see there. But what ends up happening is most real Scalding flows don't end up being as simple as that word count example. A lot of them end up being fairly complicated. Typically, most flows end up consisting of multiple steps, and they're arranged in a DAG. Each of these steps maps to a Hadoop MapReduce job. From the user experience perspective, most users end up configuring settings typically at the flow level. So if it's settings like configuring the amount of memory your flow is going to use, users will end up configuring it at the flow level, and it applies to each of the steps, which becomes a little complicated, as Gera pointed out earlier. Another thing to note is that each production flow has a unique ID, so we can look that up later as we describe our approach. So one of the things to keep in mind, since you have all these steps in a Scalding job, each of those steps can have very different characteristics depending on what you're doing. So if you're familiar with the data platform world, you probably have seen that it's similar in other systems as well. So here are a few examples on Scalding. So we've got a few examples which basically end up resulting in your heap actually requiring a lot more space. So for example, your job might actually be doing something like a hash join operation, in which case you're going to load up the RHS of your join into memory, and you're going to join that with your left-hand side. So you basically need to have enough space to hold the RHS in memory. You might do something like a sum by key, which is similar to an aggregate by key in other platforms. And then Scalding will end up optimizing that operation underneath the hood to do map side aggregation. So it's going to hold a lot of these values in memory while it's doing the aggregation. Other operations like joins as well end up resulting in a lot of data being cached, so that because that's how cascading implements the join. Even within the step, you might actually have a lot of data skew because just the way your splits end up. So you might end up with like a few tasks which require a lot more memory than the others. So they don't all have the same footprint. So given these constraints, you have users who are configuring memory settings on the entire flow level, but within the flow, you have a lot of steps, and each of those steps have very different memory settings. So what ends up happening as a result of that is that users either don't know what memory settings to end up using, or they just end up setting the wrong ones. Since, as a lot of you guys probably are familiar, software engineers, when they're not sure of how to do something, since time immemorial, they've probably just been looking at something else which works, they pick up an example that works, they copy the settings over, and they use it in their job. What that ends up leading to is like a bunch of problems. Inevitably, their job is running in production. It's good for a couple of months until they end up getting paged. Typically, you get paged at like 3 in the morning or something, and as an engineer, when you get paged at 3 in the morning, it's not a lot of fun to sit down and debug like an out-of-memory issue with your job by looking at heap dumps and stuff. It's not the most pleasant way to spend 3 a.m. So what they end up doing is just bumping up the memory settings. They either set it to the max container size, or they just set it to some value which is going to allow their job to pass. Fix it. Some of the good ones will file a Jira to follow up on it. Some of the others just don't do that. They forget about it. So this sort of state of affairs leads to a couple of scenarios which end up happening. So one of them is, if you bumped up your memory settings too much, you end up overestimating the amount of memory that you've got. So that results in terms of resource utilization. Your memory footprint grows. You're using a lot more resources than you actually need. The other scenario which might end up occurring is, even though you've set some particular memory settings, they might not be appropriate. They might be underestimating things. It might not be the pathological case where you end up running into an out-of-memory error, but it might be a scenario where you're underestimating, but your job is spending a lot of time in GC. And we've seen that on a couple of jobs on our clusters, that they spend 20 to 25% of time on GC. But again, in terms of resource utilization, what ends up happening as part of that is the milliseconds of your job increases. So again, your resource footprint is higher. So at this point in time, we can probably take a little bit of a digression to just understand a little bit about how container allocation works in Yarn, and how we can take advantage of the state of affairs to try and improve things in Scalding. So Yarn, like you guys know, is a resource allocation engine. The dimension that we are currently concerned with in terms of this talk is the memory-related allocation of containers. So in case of Yarn, this is basically done on a bunch of increments. So Yarn basically allows you to set a minimum allocation MB and a maximum allocation MB. So your container allocations is done in increments of that. So say your minimum allocation is around 1 gigabyte and you request for 4.5, you'd end up getting your request rounded up to 5 gigabytes. So when you end up requesting for containers, you're requesting for either map or reduce containers, and the sizes are determined by the MapReduce.map memory MB or the reduced memory MB settings. So you get a container of a particular size. You leave a certain amount of it aside for off-heap stuff, and typically end up setting the max heap size to around 80% of that. But the important take-home point out here is, like Gera mentioned earlier, the committed heap bytes, which is basically the footprint of your job, does not always match the max heap bytes. A lot of the times, it's much lower than that. So you can take advantage of the fact that your footprint is much lower to set the heap size appropriately. So that's kind of what we wanted to set out to do. So before we went out to do that, we decided to try and introspect and see if there was an opportunity here, given that we have some historical data. So to kind of look into this, we kind of looked at a service that we own called HRaven, which basically stores the prior job histories of all the Scalding jobs that we've run on our clusters in the past. It stores counters, it stores various other metrics that we care about. And what we ended up doing is we ended up looking at retrospectively over a month of data on HRaven to try and see if we ended up going out and setting the memory settings to the max committed heap instead of the existing heap size settings that users had done, were we going to end up saving anything in terms of memory utilization? So we tried this out on a bunch of our clusters, and it turned out that we did. There did seem to be a fair bit of opportunity there to actually save memory. So we saw that we were saving around 30 to 50%, depending on the cluster and stuff. So at this point of time, we kind of knew that, okay, we've got an opportunity to try and build a proof of concept prototype and try this out on a bunch of real jobs. So that's what we head out to do. So at a high level, Scalding needs to basically query hraven for a bunch of counters for a particular job to get the details on various steps and derive what the appropriate memory settings are. At this point of time, when we were trying to think of the implementation, we kind of knew that we'd already had an implementation that does something very similar in terms of looking up prior run history and deriving other settings, and we were using that for reducer estimation. So we basically decided to try and leverage that implementation for the memory estimation side as well. So this is what the end architecture or the end approach looks like. So on the Scalding submitter side, a user just submits a job. We end up creating the graph of the job. So in terms of like all the various steps that need to be run, we end up querying hraven to look up prior counters for prior steps, both on the map phase and the reduce phase, because the settings for those can vary a lot. Since we've got the details on the committed heap bytes for all these steps and all these phases, we can end up computing the max heap bytes for a particular step and a particular phase. We end up using exponential smoothing to kind of derive what the heap size should be. We add a little bit of a buffer on top of that to just keep it as like a safety window or whatever. And then we end up like using that to kind of come up with a container size which is aligned on a yarn boundary and just go out and set a bunch of configuration settings for each step, and hopefully that'll work. So we were able to try this out on a few jobs. One of them was Gera's job. So these jobs are already fairly tuned. Gera and his team are very well tuned in the dark art of Hadoop optimization. So we weren't expecting to find a whole lot, but we actually did end up seeing substantial savings even on Gera's jobs, which were fairly optimized. So as you can see on the left, we've got the megabyte milli numbers from when you're not slimming the jobs, and then when you end up using this algorithm to actually slim the jobs, you end up seeing that you're saving around 30% in terms of your resource utilization, megabyte millis. So we ran the math on this. It turns out that this single job ends up saving around 140 node hours. So when you extrapolate that to the entire pipeline that Gera showed earlier, and we tried to run the math on like if we were to run this on AWS, we would end up saving around $1,000 a day, which ends up being like around $365,000 odd for the entire year. And that is just for one pipeline. So if you roll this out to the entire cluster, we have a lot more queues, a lot more users. So there's fairly substantial savings there. So we are currently in the process of rolling this out to many more users and stuff. So hopefully we should have some more numbers there. So I guess at this point, it's probably a good idea to sort of think about why this process is hard. So here are some of the challenges and some of the questions that we are trying to answer in the coming weeks and months. So we need to have some sort of fallbacks in case of failures. Failures can come in various forms. We could run into issues when we're trying to talk to the history service. The history service might be down. We need to be able to recover from that. We might come up with a memory estimate that's inaccurate. So the situation that I talked to you about with respect to like running into out-of-memory issues, we might come up with a memory estimate, and a user's job still runs into an out-of-memory issue. So our estimator needs to be able to recover from that and handle that. The other scenario is that since we're basing this estimate on historical runs of a particular job, the reality is that users' jobs change a lot of the time, right? It's not like you've written the code for a job and you're just going to let it be statically forever. A lot of the times you're going to re-architect the job, you're going to rewrite the job. In which case, there's something that we have to think about around, is that estimate still valid? So if you had like 3 steps in your job and you've rewritten your job completely and there are 5 steps now, is that estimate still valid? So that's something that we have to work on. The other aspect that we kind of alluded to earlier as well was like, how do we handle situations where we could be underestimating, but we're still not running into OMs. So we need to account for handling GC time as a fraction of like CPU time as well. So we've got a PR up, which has been out since a couple of weeks now. So if you guys are excited about this, feel free to jump in on the PR. Suggestions, contributions, and stuff are welcome. So the work that we have talked about today sort of fits into a larger project and a larger initiative that we're driving at Twitter that's around auto-tuning in general. So what we've seen as a platform team is a lot of users end up coming to us, and they're not sure of a lot of settings with respect to MapReduce jobs. So at Twitter, there are MapReduce-related settings, there are Scalding-related settings, and sometimes there are even cascading-related settings. So users a lot of the times are not sure of which knobs to tune. Some of these kind of fall into three major buckets. So one of them is kind of around memory estimation. How do you estimate how much your container sizes and heap sizes should be? The other two are around adjusting your split sizes so that you end up with the appropriate number of mappers. How do you end up setting the right number of reducers so that your jobs don't take forever? So these three sort of broad initiatives are kind of being combined into sort of a single framework that we're building around auto-tuning. And Anton, as Gera mentioned, is sort of leading that effort, and he's sitting right here, so you can talk to him after the talk if you're interested. This framework is also going to allow us to handle situations like a lot of settings are competing. So in case of Scalding, if you're doing something like map side aggregation, that ends up requiring buffers on the map side. But that ends up conflicting with some settings that you end up using on the Hadoop side, like IO-sort-MB. So we want to have some way of handling these sorts of competing settings as well. Another area of future work that we are looking into in the coming weeks is integrating with multiple history backends. So we got to push within Twitter to start picking up and rolling out ADS-V2 within the company. So that's something that we're actively looking to integrate with in terms of getting additional metrics and additional counters and stuff that we would be interested in. The last dimension in terms of future work is to experiment with, say, machine learning-based tuning for a lot of these competing settings, because there's no good and easy heuristic for a lot of them a lot of the time. So we have poked at this a little bit in the past, and that's something that we want to explore in the future as well. So there's a lot of interesting work to be done there and a lot of interesting challenges, and we are looking forward to sharing some of them with you guys in a future talk. So in conclusion, auto-tuning is hard. A lot of the times users just don't know what the setting should be. They find it really hard to end up doing that. But when you end up doing it, there is a huge opportunity for potential resource saving. So if you do auto-tuning right, there is a lot of opportunity there to end up saving resources at a very large scale. But that said, you need to be really careful about how you end up doing automation, because that process that you're ending up rolling out could adversely affect user jobs. So you have to do it in the right way so that it's fail-safe. So that's kind of all we have for today. Thanks for listening, and we take questions if you have any.
Any question?
Yeah.
So are you able to keep metrics on non-heap memory that's used?
So, do you want to take it?
Go ahead. Yeah, I don't think we.
Repeat the question.
Sorry?
Repeat the question.
Yeah, I can repeat the question. So I guess the question was, do we have metrics on non-heap related counters and stuff like that, right? As far as I know, we don't at this point of time, but that's something that we could potentially look into in the future.
There are some MapReduce counters that give you insight into this. You have physical memory bytes that tells you how many memory resident pages you have. And so you can sort of correlate the heap size and the non-heap size based on that. It happens not to be as important in classical MapReduce framework. Only on the reducer side, you have native buffers for the shuffle. On the map side, there's almost zero native overhead. However, there are a lot of teams at Twitter that have their own implementation of like where they retrofit a machine learning library into old Hadoop streaming, and these jobs actually end up completely off heap. And so yeah, we can only estimate it using this method, but so we hope to do more in this future as the need arises.
Yeah, so the question was, we're currently focusing on memory, and are we planning to generalize this to CPU as well, right? Yeah, that's definitely something that we want to do in the future. We currently don't end up like allocating on our yarn clusters by CPU, but that's something that we are rolling out in the coming months. So that's something that we would definitely end up like looking into.
Go ahead.
So I guess the question was around, so if a job code changes, it's easy to invalidate the runs, but if the input changes drastically, how do you handle something like that, right? So we've kind of used a couple of strategies which have worked, at least for reducer estimation. So we end up using input size ratios. So it's again an estimate. So we use input size ratios to kind of get a sense of like, okay, if you start off your input with like X gigs per like mapper or whatever, and now it's gone up to Y gigs per mapper, maybe we need to scale the numbers a little bit. So we have a ratio-based setup for something like that. But that doesn't handle the situation where like, your input size in terms of bytes stays the same, but the structure changes drastically. So you have like really large lists and stuff. So that's something that we probably should look into, but we've not currently got that on our plans.
Yeah, and I would like to add that most of the time these changes don't happen overnight. It's an organic growth that is slow, and so these trends are already represented in the time series stored in H-framing, and the smoothing, exponential smoothing takes care of it actually naturally. So I guess that's why people use it. Yeah. Go ahead. Right. So the question is whether we have more detailed statistics about sort of distribution of different heap areas and the GC. So far, no. We only store what MapReduce framework provides out of the box, which is the GC time millis and CPU time millis. So you can draw conclusions from that. But now that ATS v2 will come about, we can easily export all the JMax metrics that are exported by each task JVM. Oh, thank you.
So I have a question is that right now this framework is only support for MR jobs. So is there any chances that it is able to like supporting other framework? Because we did encounter the similar issue with Apache Samza.
Right.
So our Samza container is really big because it needs to handle those additional bursts from Kafka side.
Right.
We have to set up really large containers in place.
Yeah, so I guess the question was, is there a plan, or are there plans to basically extend this to other frameworks apart from MapReduce, right? So at this point in time, we don't have any plans particularly around this project to extend it to MapReduce, beyond MapReduce. But we would potentially like think about that if we were to like pick up other projects and stuff as well.
So I think we saw a lot of similarities with TAS, especially if you where we can immediately apply the same technique once you disable the JVM reuse, which some people really love, but for us, we end up running a lot of, we think it's more optimal to run at scale without JVM reuse, and then it's directly transferable, this technique. But if for other more complicated containers like Spark, so we need to come up with a completely different way how we implement this. But the technique of actually collecting counters and analyzing the time series will be the same. Are there any other questions?
Great, thank you.
Thank you very much for coming, and please rate our sessions. Conference organizers appreciate your feedback.